Alright, next up is a video about limits involving infinity. Now when I say limits involving infinity, they can basically be one of two types. They can be limits as x approaches infinity, or they can be limits as x approaches a number that are infinity. So we'll look at both in this video. This video is not going to be an algebraic connection yet. We are going to do all the algebra stuff next in a different video. But this is all about graphing, right? Making connections to limits with a graphing approach. So my previous two videos, an introduction to limits and a graphical limit worksheet, are two that you definitely want to look at first before you watch this one. So here we go. I have a piecewise function on the screen and 4 questions below it. So let's start. The limit of the function as x approaches 1 from the left. 1 from the left. So we're going to find 1 on the x-axis and approach the function from the left of that. As the function comes in from the left and the x value approaches 1, the y value seems to get close to positive 1 as well. From the right-hand side, the right-handed limit as x approaches 1 from the right-hand side, the function approaches positive 2. Which means the overall limit, since these don't agree, the overall limit does not exist as x approaches 1 generally. The function value when x is 1 is the closed dot, positive 2. Now if I were to ask you what's the limit of the function as x approaches positive infinity? Well, as x approaches positive infinity, we're going that way, the graph is a constant at 2, so that answer is still going to be 2. If I ask you what's the limit of the function as x approaches negative infinity, so we're talking this way now. As the graph gets as the x values get really small, the graph goes down infinitely. So it's going to decrease forever, which means it's going to approach negative infinity. Moving on. Number 2. The limit of the function as x approaches 1 from the left. So 1 from the left-hand side comes in this way. It's negative 1. I'll go a little bit faster here. 1 from the right-hand side is positive 1. They don't agree, so the overall limit does not exist. The function value at 1 you can see is a closed dot at 0. Alright, moving on. The left-handed limit as x approaches 1 from the left is positive 1. We're looking at some sort of absolute value function here. 1 from the right, same thing, it's positive 1, which means the overall limit is 1. The function value at 1, however, is an open circle. It's undefined. If I were to ask you what the limit of the function is as x approaches infinity, it gets infinitely small. It's going to continue to decrease forever. The limit of the function as x approaches negative infinity, so the x values just go left forever. They also go down forever, negative infinity. As the x values get smaller, the y values get smaller. I think we just answered that one. Let's go on to the next one. Number 5. The limit of the function as x approaches 0 from the left. So it's this way. Number 0 is right here. So that answer is positive 1. From the right-hand side, it's positive 1, which means the overall limit is also 1. The function value at 0 looks like it's 1 as well. Let's move on. Here we have an asymptote at positive 2. As the function approaches 2 from the left, we're going up this way. It approaches positive infinity. Goes up forever. As it approaches 2 from the right, it goes down forever, negative infinity, which means the overall limit does not exist. The function value at 2 is an asymptote, which means it does not exist. If I were to ask you the limit of this function as x approaches positive infinity, so as the x values get bigger, what happens to the y values? It looks like they infinitely get close to 0. Looking at as the x values get infinitely smaller, so as the x values get infinitely smaller, what happens to the y values? So it looks like they also kind of squeeze down to this horizontal asymptote at 0 as well. Number 7, vertical asymptote at -2. So from the left-hand side, we're going to go up to infinity. Right-hand side, we're going to go up to infinity, which means the overall limit is infinity. The function value does not exist. Moving on. Number 8. Here we have an asymptote, but we also have some sort of crazy value there. This is kind of rare. So from the left-hand side, it's infinity. From the right-hand side, it's infinity, which means the overall limit's infinity. But the function value is defined at 0. So again, the limit does not have to equal the function value. The limit means what's the graph getting close to, not necessarily touching. Number 9. So here we're going to look at the limit of this function as x approaches -infinity. So as the x values get smaller and smaller, what happens to the y values? Well, they get bigger and bigger. How about the limit of the function as x approaches positive infinity? As the x values get bigger and bigger, the y values get bigger and bigger. In other words, they never stop increasing. Number 10. The limit of the function as x approaches -infinity. So as the x values get smaller and smaller, the y values get bigger and bigger. The limit of the function as x approaches positive infinity. So as the x values get bigger and bigger, the y values are going to get smaller and smaller. Number 11. As x approaches positive infinity, so the x values get bigger and bigger, what happens to the y values? It looks like they kind of squeeze into this horizontal asymptote here. So that would be +1. They're squeezing into this horizontal asymptote. As the x values get smaller and smaller, the y values seem to squeeze towards this horizontal asymptote at -1. Number 12. We have some sort of trig function here. Looks like some kind of sine function with maybe like an x underneath it or something. As the x values get bigger and bigger, what happens to the y values? Well, it's a little bit tough to see, but I think the y values are kind of like following some sort of curve this way. It's kind of tough to see, but if we kind of see that these graphs are, or these y values are kind of sandwiching in between an imaginary line here at 0. So I would say that that's 0. Same thing over here, right? These are kind of squeezing down to the x-axis. A little bit better look at it here. I graphed it a couple more times. Well, I'll come back to that actually. Let's do this one. Here we have the basic function 1 over x. All right, if I ask you the limit of that function as x approaches, I don't know, 0, you would say that it does not exist, right? As the function comes in from the left, it goes down, from the right it goes up. The limit overall at 0 does not exist. There's no function value at 0 either. If I were to ask you what's the limit of the function as x approaches, I don't know, maybe positive infinity, right? So we're going, as the x values get increasingly bigger, it looks like the y values kind of squeeze down to the horizontal asymptote of 0. Over here, as the x values get infinitely smaller, they go this way, they also approach 0. Alright, if we were to do one-sided limits, as x approaches 0 from the left, x approaches 0 from the left, it's -infinity, and 0 from the right, it's positive infinity. Since they don't match up, the overall limit does not exist. Alright, so here's a really good example of how functions involve infinity because their limits are infinity, or they can approach, their x values can approach infinity. Alright, let's come back to our good old friend, the x squared graph. If I ask you what the limit of the function as x approaches infinity is, so as the x values get bigger, what happens to the y values? Well, they just keep increasing as well. How about the limit of the function as x gets really, really small? as x approaches negative infinity, our y values are also going to keep increasing. As the x values go left, the y values go up. Let's come back to this trig function. Looks a little bit like the one we saw above. So here we have sine of 2x over x. I'm looking for the limit of the function, I'll write it down here, the limit of j of x as x approaches infinity. Alright, it looks to me like they're kind of following some sort of very basic path. And the path is, notice these amplitudes are getting smaller and smaller. These amplitudes are getting smaller and smaller. They're squeezing together, which means they're approaching 0. Different look at that graph, that same graph. I kind of zoomed out a little bit. You can see a little bit better. All right, you can see that these values are squeezing towards the middle. They're squeezing towards the middle. If I zoom in on that, it's kind of easy to see. All right, they start off here at about 0.25, and they go maybe to about, I don't know, if that's a quarter, that's got to be look like an eighth or something like that. And they get smaller and smaller and smaller. All right, if we were to put these little lines, you would see that those little lines increasingly get closer and closer to 0. Same thing down here. All right, these lines are increasingly getting closer and closer to 0. So if I were to take the graph out of there now, you can see that they definitely are trending towards that point right there at 0. Another look at it here, it's a little bit better look, I think, too. You can see that they are squeezing together. They're squeezing together. All right, so that takes care of it. That's our, I guess, our third video on finding limits graphically. We're going to move into an algebraic discussion next, and then we'll get into some continuity questions, and then move on to some derivatives and some actual differential calculus. So thanks for watching.